to record this since we're missing so many people. I'm going to share my screen. So this is what I want. So today, like I said, we're going to talk about type 7 problems. And these are the miscellaneous problems. Problems that show up often enough that we need to talk about them, but not so often that they get their own category. And they really fall into two categories, one of which we've kind of already looked at a bit, or at least it's come up. But those are implicitly defined relationships or relations, and therefore implicit differentiation. So we've already talked about, even in the work that we did yesterday, about implicitly defined relations. That's when, you know, we had something like, I think we had this yesterday, dB dt was equal to 1/5 b minus 7. I don't know, I'm making it up, okay? Where b is a function of t. But when I might take a second derivative of this, I have to remember that b is a function of t and use implicit differentiation. So we've touched on this a little bit. We're also talking about the types of functions that look like this, where I can't really easily solve that, although in that case I might be able to solve it for y. Let me make it a little harder. Okay, where I can't easily solve that for y, but I still want to know what dy dx is. So you should be able to take a first derivative using implicit differentiation, take a second derivative using implicit differentiation, substitute points into both of those types of equations so that you can tell me things like whether the function is increasing or decreasing, whether it's concave up or concave down. You should be able to figure out if there are horizontal or vertical tangents. You should be able to write the equation for the line of those tangents. And then again, finding extreme values, which has to do with the first derivative. So basically all the stuff that we've been doing all year. The second category here is related rates. And we talked about this in chapter 5. And so those were the type of problems where an object is moving, excuse me, an object is moving through space. The x direction changes at one rate, the y direction changes at another rate, but I want to know how the distance from the origin is changing. So you need to be able to set up and solve related rate problems. Another example of that is the radius of a beach ball as you're blowing it up is changing by a certain rate, some dr dt. But I want to know at what rate the volume is changing, or I want to know at what rate the surface area is changing. You need to remember how to differentiate with respect to time. So if we went back to this equation up here, remembering that b is a function of time and using the chain rule or implicit differentiation. Another part of this is to interpret your answer as part of the problem. And way back in chapter 5, we had a whole list of ways to solve related rate problems. And that was part of it, is make sure that your answer makes sense within the context of the problem, and be able to explain your answer in terms of the context of the problem. And again, we've done a little bit of this. I can't remember, but it's been in the last week or so where you find a derivative of something in an AP problem, and then it says, well, tell me what this means. Okay. And then remembering to carry your units through. That can be part of this as well. Okay. So just like we've been doing all along, I have problems for you to try. So we'll see how many we get through. And then there's the homework that we will figure out. So if we go here, did I distribute problems, homework, problem type 7?
No.
Okay. Then it's there. I apologize for that. It'll take a minute. Review material. Yeah. Whoa! Not what I wanted to do. Cross notebook distribution. Okay. Sync. Okay. So we are going to start here with 2016, number 4. Yep. So I'll leave you a few minutes to work on this. If you need to start, I'll leave this up here for a couple of minutes in case you're still syncing up and you want to start looking at the problem. Okay. So I'll give you about, we'll see. I'll check in with you in about 8 minutes or so. All right, how we doing here? Do you need more time? Do you remember how to do Euler's formula? I thought we'd have to go through that. So what I'm going to do is I will share my screen, and here are the answers. If you want to start checking as you go through and see if maybe you can figure out things that you need to think about.
I have a quick question.
Mm-hmm.
So for the part A, obviously I distributed, like, the first one is like 2x minus 1/2 y dy dx. So I put the dy dx and distributed, but I got 2x minus 1/2 x squared y plus y over 4.
Nope. Here.
Wouldn't you distribute the y?
So you've got dy dx is equal to x squared minus y over 2, right?
Mm-hmm.
Okay, so remember, and we've talked about this a couple of times, that I'm taking the derivative of that with respect to x, right? So this is going to give me 2x, right? Minus, I've got a half, and then the derivative of y is
would be dy dx,
right?
but
It's 1 times dy. Whoa.
why don't you, what, like, 'cause in some cases don't you have, you leave the y and then you do dy dx next to it?
Well, that's why I'm asking you what the derivative of y is. So if you have a variable to the first power, then the derivative is 1, right? If I asked you what the derivative of x was, what would you tell me, Jacqueline?
Well, if it's just that, then it's 1.
Right.
Yeah.
So,
Oh, so
okay.
okay. So if it's y to the power, that's when it's
Right. If
different.
it was y squared, then I take the derivative. That would give me 2y. But then it's really using the chain rule because
Okay.
y is a function of x. So then I'd have to multiply it by dy dx.
Okay.
It's
Okay.
the same principle whether I'm doing it up here in the context of the problem or I'm doing our little example down here.
Okay. Okay.
All right. So, and then here you're just gonna substitute in. So you've got minus a half, and then you put in dy dx again.
Yeah. Okay. Yeah. That was my only problem, was that I just was
Okay.
the y part weirdly. And could we go over c too?
Let's hang on and see if anybody else needs to catch up.
Okay.
Okay. How are we doing, guys? Are we good? Has everybody tried A, B, and C? I'm seeing some yeses. Does anybody need more time to work on A, B, or C?
Dr. Guess,
Mm-hmm.
I just had one question to clarify B. So I plugged in the point for the first and second derivative of dy dx.
Yep.
So I got 0 for the first derivative, which means it's a critical point, and then concave down for the second derivative. Is that all we need to determine its relative maximum, or do we need to know if it's increasing and decreasing as well?
Nope. That is enough to justify that.
Okay.
Wow, I did a lot of extra work for nothing.
It's all right.
Okay.
All right. So we've done A. We've basically talked about B, or Lauren gave our answer for B. Okay, so now we want to talk about C. So C is to find that limit. So I've got y is equal to g of x, and I know that g of negative 1 is equal to 2, so that kind of gives me a point. And then I want to find the limit as x goes to negative 1 of g of x minus 2 over 3 times x plus 1 squared. So this is a great opportunity to review. So number 1, you have come to a limit. What is the first thing you do?
Plug in.
Plug in, because maybe you're going to get lucky, right? So if I plug in, this gives me g of negative 1 minus 2 over 3 times negative 1 plus 1 squared. So I'm going to get 0 in the denominator. And in the numerator, I know that g of negative 1 is 2. So actually, I get 0 over 0. So when you take a limit and you get 0 over 0, that tells you something really important that you can do and that you can use. So what can you employ at this point?
L'Hopital's rule.
L'Hopital's rule. Okay, which I don't think we have come across yet to review, so this is a great time to put that in there. So L'Hopital's rule says that if the limit as x goes to, I don't know, we'll call it a, of f of x over h of x is equal to 0 over 0, or other things, but this is what's important here, then that means that this limit is also equal to the limit as x goes to a of f prime of x over h prime of x. Okay? It is very important that you still include that limit there. We are not saying that the limit as x goes to a of f of x over h of x is equal to f prime of x over h prime of x. That is not what I am saying in any way. You must keep the limit in there. And what this is also saying is that I take the derivative of the numerator and leave it in the numerator, and separately I take the derivative of the denominator and leave it in the denominator. Okay. I feel that when you get to a situation where you're taking a limit and you have 0 over 0, that you really need to write that you are using L'Hopital's rule. Okay, just as I feel strongly that you need to write that you're using the mean value theorem or the intermediate value theorem, you need to say, I recognize that somebody else figured out what to do and I am applying, and it's always a his because that's just the way it works, I am applying his rules. Okay, so this tells me that I've got the limit as x goes to -1, and now I can take the derivative of the numerator. What's the derivative of the numerator going to be?
Is this the same, like going off the same, like, is like the one mentioned the differential equation at the very beginning? This is supposed to be the original function for that?
Not necessarily.
Okay. So
But what's the derivative of g of x minus 2 going to be?
G prime of x.
Yeah, g prime of x. Okay. And then what's the derivative of the denominator going to be?
6 times x plus 1.
Yep. 6 times x plus 1. Okay. And then, yes, it does actually say that y equals g of x is the particular solution to the given differential equation. So that means that I can come over here and say, that's not the color I want to use. I can say that g prime of x is equal to dy dx. And it's the same dy dx that I had in the beginning. Okay. So this is going to be equal to the limit as x goes to -1 of x squared minus y over 2 over 6 times x plus 1. And again, I've come to a limit. And the first thing that I do is I substitute in. So I'm going to have -1 squared minus, and y is going to be equal to 2. 2 over 2 over 6 times -1 plus 1. And what am I going to get?
0 over 0.
0 over 0. Which means that, again, I can use L'Hopital's rule. even though that does not look like L'Hopital's rule. So again, I'm taking the limit as x goes to -1. I'm looking at this over here. Actually, I'm not going to look at that. I take that back. I'm going to look at this. Okay. So what's the derivative of g prime of x going to be?
G double prime of x.
Yep. So I'm going to have g double prime of x over, and what's the derivative of the denominator going to be? 6. Okay. So g double prime of x is going to be my d2x dx squared. And I have an equation for that, which is (2x minus x squared over 2 plus y over 4). That's a y. And when I substitute in my x equals -1 and my y equals 2, I get -1. I'm sorry, I don't. I get -2. I've still got my 6 in the bottom, and that gives me -1/3. Okay, we good? All right, so I'm going to, oh, go ahead.
Sorry, I have a quick question. I don't know why I'm making these, I must be making simple math error, but like when you distribute for the first 1/2, like the one that's like when you plug into x squared over 2, since it's -1, like the negatives cancel out, so.
No, they don't.
It's
-1 squared is equal to 1.
No, I mean, oh my God, I didn't put the squared in. Okay. I'm sorry.
Okay. All right. So I'm going to assume that we need to go over part D to remember what Euler's formula is. Yes? Okay, I got at least one yes there. Okay, so this is part D. So part D says y equals h of x be the particular solution to the differential equation with h of 0 is equal to 2. Using Euler's method, starting at x equals 0 with 2 steps of equal size, find h of 1. Okay, so when we did Euler's method, what we did is we started with a point, and our point here is 0, 2, because that's the point that we're given. And remember that the whole idea with Euler's method is that I move a little bit in x, I figure out what that means in y, how that changes my y value, I come up with a new ordered pair, and that starts my process over again. So if the first thing I have to figure out is what my delta x is going to be. How far am I going to move over in x? Now I need to get from x equals 0 to x equals 1 because they give me this point and they want me to estimate it for x equals 1. And they tell me to use 2 equal steps. So how much do I have to shift by if I'm only going to make 2 steps to get from 0 to 1? 0.5. Okay, so my delta x is going to be 0.5. A big part of Euler's method is saying, and I'll go over here and write it, that estimating or assuming that dy dx is equal to delta y over delta x. That I can approximate delta y over delta x is dy dx, or the other way. Okay, and then what we say is dy is equal to dy dx times delta x. And that's what I'm going to write in up here. So remember that dy dx is equal to x squared minus y over 2. So I've got this point 0, 2. I'm going to substitute it into here, into my dy dx. And what is that going to give me?
Zero 0.5 x squared minus y over 4.
Well, I'm using this point. There's no delta x in this equation. There's only x's and y's. So what's x equal to?
0.
Yeah, and what's y equal to?
2.
Right, so this is going to give me -1, right?
Mm-hmm.
And I'm going to multiply that by my 0.5. So my delta y is going to be -0.5. And then I come up with my new point, which is x plus delta x, comma y plus delta y. So I'm going to take 0 plus 0.5. That's going to give me 0.5. And then I'm going to take 2 plus -0.5. And that's going to give me 1.5. And I'm not to x equals 1 yet, so I bring that new point over here, and it becomes my starting point for my next iteration, my next increment. So my change in x is still 0.5. But now I have to take these new points and substitute them into dy dx. Because my delta y is dy dx times delta x. So what do I get for dy dx when I use my point 0.5 comma 1.5? -1/2. My delta x is 0.5 or 1/2. And that gives me -1/4, or -0.25. So then my new point is x plus delta x, which is going to give me 1, comma y plus delta y, which is going to give me 1.25, or 5/4. And so h of 1 is going to be 5/4.
Is it bad if we put 1.25?
No.
Okay.
Okay, we good? All right, so let's look at OneNote. What I would like you to do for homework, hang on, my OneNote froze again. What I would like you to do for homework is 2015 number 6, which is the second implicit differentiation problem, but it's up at the top because it's the class problem. Okay, so it's the next thing in your notebook. And then do the homework problem down here, and I believe that is 2004, that is related to implicit differentiation. So as soon as we're done here, I will update the portal, but it's 2004 number 4, kind of the first homework problem there, but it's also the second in-class problem. And that means that when we get together on Wednesday, we can just go over the related rate. We can go over these if we need to. You can check your answers and then we can do the related rate. And we should be all set. Okay, and then Friday we'll just kind of finish things up. All right, and like I said, I will update the portal as soon as we sign off here. Okay. All right. Any questions about anything? Okay, then you may go, and I will see you somewhat tomorrow, but on Thursday for class. Bye.